Okay, welcome everyone. Welcome to Delft. Welcome to this beautiful building, the Green Village, where we have our conference today. So my name is Matthias Möller. I'm together with Sebastian Feld, co-chair of this year's edition of the PowerWeb conference. And well, I think for us it's a very great pleasure to welcome you all here, to welcome you to this conference, which has as a theme, which is not printed here, I should go back, sorry for that, AI and quantum computing for the energy systems. And I think everyone here has encountered AI already, be it on the smartphone, be it when you talk to the KLM hotline, you always end up at an AI, sometimes not too intelligent system. Yeah? But quantum computing is maybe something which is new to some of us. And well, I personally think quantum computers or quantum computing is a very exciting emerging compute technology. It's not too industry ready right now, but it has a lot of potential. And today we have invited several experts in this field from the different disciplines to talk about the opportunities, but also about the challenges of AI and of quantum computing for the energy system. And without stealing more time, I would like to ask Professor Peter Palensky, the chair of the PowerWeb Institute, to the stage to officially open this conference. So Peter, please.
Thanks, that sounds very festive, officially open. Yeah, thanks everybody for coming on this beautiful sunny day. Who knows what an institute is? That's a mysterious, it's a cross-departmental organizational unit. Departments are narrow spectral lines of knowledge and coverage. And the moment you have a topic or a sector or a question that needs different viewpoints, you can set up an institute. Yeah? There are institutes for transport, for instance, and institutes for, I don't know what, hydrogen. PowerWeb is an institute for intelligent, integrated, and inclusive energy systems. That's very broad. Huh? Energy alone means you have heat and gas and electricity and steam and I don't know what. Of course, electricity might be the dominating backbone of this entire party, but the other carriers are not unimportant and they offer quite some options. Yeah? And intelligent, integrated, and inclusive also means you have algorithms, you have conversion, you have people in the loop. So it's pretty broad. Huh? But that's how the world is. Outside, the world is connected, and we cannot look at that problem of making our energy part of our lives sustainable in a monodiscipline way. So we team up. We have different faculties involved: aerospace, mechanical, AV, TBM. So they're all chipping in to help. Out of these faculties and departments, individual scientists team up in PowerWeb, and it's extremely productive. It's extremely successful. This is the annual conference, so once a year we meet and we pick one of the many aspects, one of the nuggets in our larger problem statement as a topic. This year it's advanced computation or quantum and AI for the power system. The romantic hope that we have is that quantum computing and AI can help with dealing with the complexity of the power system, of the energy system of the future. You have to combine orthogonal data coming in. You have scalability questions. You have exploding numbers of options and faster decisions to do. So we believe we need every help we can get. And today we gather the fantastic lineup of speakers. I think our chairs, Matthias and Sebastian, will guide you through the day today, where we present latest research, pose new questions, and we really want it to be interactive. So this is really a meeting point here. It's not a TV show that you watch and consume in one direction only. No, this is an interactive meeting, and I hope something comes out. If you come with new ideas and new questions, that's even better. That's all from my side. So my job is done for now, so I can enjoy. Thanks a lot for being here, and let's see what the day brings. Thank you.
Thank you, Peter. Well, so you said it's not a TV show. Definitely it's not a TV show. It's an interactive thing. So we have 2 great keynote speakers, one that we just start in the morning, and then after that we have a short break, and then a couple of shorter presentations about the different research labs, research aspects we do here at TU Delft. And after that we have the lunch and a poster session. So you see already a couple of posters here on the right side of the hall. Yeah, so I kindly invite you to have a look at them during the lunch break. And then in the second part of the day, we start with something which is really interactive, a panel discussion where we have invited a couple of people that come from different disciplines and have different viewpoints on the problems, but also on the possible ways to solve things. And well, I hope we really get an interactive discussion there. And then we have the second keynote presentation by Professor Koen Koek on the AI aspect. So we start in the morning with the quantum computing aspect. And well, then we come to the closing and hopefully some Borrel and networking events. Well, that's the only thing that reminds me a little bit of a TV show, because such an event is not possible without sponsors. So this is the commercial break. We are very, very thankful to our sponsors. So first of all, to mention the Green Village where we are, that are hosting us, but also Quantum Delta Delft, which is a part of the bigger Quantum Delta NL, so the Dutch quantum ecosystem community, QTech, the joint venture between TU Delft and TNO, Convergence, and the Institute for Computational Science and Engineering from TU Delft, who all contributed to this this conference, and I would really like to thank them for all their financial and other support. Let me introduce our first keynote speaker, Thomas Morstyn, who is an associate professor at the University of Oxford. He holds a degree in electrical engineering from the University of Melbourne, and a PhD from the University of New South Wales. He's an expert in power systems, in power system control, in power system optimization, and on top of this, in quantum computing. So he kind of opens with the first part of the theme, AI and quantum computing. And well, Thomas, I'm very happy that you're here and that you will talk about the opportunities for net zero made possible by quantum computing. So, the stage is yours.
That's perfect. Okay, great. Thanks very much for that kind introduction. All right, so I'll jump into things. So today I want to talk about some opportunities from quantum computing for net zero power system optimization. So as mentioned, I'm from the Department of Engineering Science in the University of Oxford. All right, so a quick overview of the presentation. I'm going to start by talking about power system optimization across different scales. Discuss net zero and some of the new sources of complexity that we're facing. Talk about opportunities from quantum computing then, and I'll talk about a case study of kind of initial work that we've done looking at quantum annealing for combinatorial optimal power flow, and then finish off with some conclusions and future research directions. All right, so power systems are undergoing a fundamental transition as we try and move towards net zero carbon emissions. And there are some major technology trends within this. So one is the widespread integration of distributed renewable generation. Another is the electrification of heating and transportation. And then a third is the integration of consumer-level ICT infrastructure. And so this creates the kind of new opportunity for granular sensing and coordination within the power system. So this creates some opportunities, but also some major unresolved challenges for both operation as well as planning the system. So one issue is that the energy markets, most countries have, were designed for coordinating a few thousand large power plants, but now in the future we could potentially have millions of individual owners of grid edge devices, things like electric vehicles, heat pumps, batteries, and so on. Also, this means that flexibility is increasingly moving away from the supply side towards the demand side and is going to be embedded in local distribution networks. And these distribution networks are more extensive and also have more nonlinear characteristics than transmission systems. And then our supply is becoming more variable and more uncertain as well. All right, so a core sort of problem for power system engineers is the optimal power flow problem. So the goal here is to solve an optimization to schedule generation to meet demand at lowest cost within the network constraints. So network constraints can be things like voltage limits, power flow limits, and so on. And the optimal power flow problem underlies a lot of the optimization applications that we're interested in the grid, energy market dispatch, but also earlier unit commitment, where we're scheduling which generators will run or not run, and then also years ahead of time when we're thinking about planning expansions to the grid, whether those are new transmission lines, new generators, and so on. Now, even without net zero, there were already some challenges with this problem. So, AC power flows are nonlinear, so it's a kind of complex optimization. Also, power networks have very fast dynamics, so it means that, when a power injection changes in the system, it very quickly affects all of the other buses in the network. And then any imbalances can lead to blackouts, which have this extremely high cost, both for sort of the economy as well as human health. And governments usually have some extremely high reliability targets. So in the UK, for example, we aim for a 3-hour loss of load expectation per year. So this is something like 99.97% reliability target, right? All right, so these kind of optimal power flow problems become even more complex when we want to include discrete decisions in our problem. So these come about because of unit commitment, so if we have startup costs or minimum on and off times for generators. Also, if we have discrete sources of flexibility, so for example, if we have electric vehicles or heat pumps with on-off control, when we have network upgrade decisions and also generation placement and sizing decisions, usually these are not continuous but have some significant fixed costs and maybe some limited sizing options. And so this then creates a bunch of kind of yes-no decisions, which means that we have a decision space that grows exponentially and is very difficult to deal with. Okay, so more broadly, there's actually a range of different optimization problems that people want to solve in power systems, and they vary across these temporal scales from years ahead to minutes ahead of operation, and from spatial scales from local distribution feeders up to national transmission, right? So long ahead of operation, we have these expansion planning problems. You can think about the transmission planning, but also there's distribution network planning and increasingly microgrid planning. So for example, if you're doing a smart campus, you have to make decisions about how you're going to do that. Then for the energy market, we have transmission and economic dispatch. But increasingly, countries, including the UK, are introducing local energy market mechanisms. So local energy markets or local flexibility markets, and this creates new local economic dispatch problems. And then to manage distributed resources, often we're trying to form things like virtual power plants or energy communities. And then we have both a kind of formation problem, where we have to form a virtual power plant coalition, and then also a control of that coalition closer to real time. And then individual sites have energy management systems. So people talk about, microgrid energy management, building energy management, home energy management, and battery management systems as well. All right, so within that kind of picture, then net zero adds a bunch of computational challenges to all of these different problems. So I talked about already this idea that we're introducing potentially millions of controllable devices in the form of these grid edge resources, electric vehicles, heat pumps, and so on. And this is then also making the transmission-distribution interaction much more important. Previously, we could kind of think of distribution as a bunch of lumped loads that we could kind of ignore, but now we have to really think about the details of the power flows within the distribution network. Energy storage introduces time coupling, and then also batteries in particular tend to have very nonlinear degradation and efficiency characteristics. Uncertainty is increased by renewable generation, and so we want to introduce optimization problems that are uncertainty aware, things like chance-constrained optimization, which is more complicated. And then also in the UK, as well as the EU more broadly, there's the aim of significantly reforming energy markets to sort of update them for net zero, right? But when we're thinking about market reforms, that also then creates a bunch of difficult modeling and design problems. Often we want to understand whether participants in the market might have strategic power to be able to manipulate prices. And so often this creates these kind of multi-level game theory optimization problems, which are also quite complicated. All right, so before we get to quantum computing, there's a lot of innovation, right, that's already happened in classical optimization, and there are approaches that people have looked at to try and scale up classical optimization approaches. So we have linear power flow approximations. You know, the DC power flow approximation is well established in transmission networks. For distribution, things are more complicated because the networks are more nonlinear, which means that the linearizations tend to be more operating point dependent. Also, people have developed convex relaxations. So we have a second-order cone programming relaxation that's exact for radial networks under certain assumptions, and a semi-definite programming version of meshed optimal power flow, which also, you know, is exact under, you know, certain conditions. And so these, you know, create significant increase in scalability, but they don't totally solve our problems because these methods, even though they're convex, actually they can still be quite complex to solve in practice. And then there's been a lot of innovation around distributed optimization. So trying to kind of take our big optimization problem and break it up into small problems and then solve the big problem through some kind of iterative convergence process. Here, you can get a lot of mileage out of this, but you tend to have some limit to how much benefit you get from more and more, you know, smaller subproblems, because you have this kind of communication or convergence overhead. And then also, you usually have a trade-off between the time it takes to converge and the accuracy of the solution that you end up kind of hovering around. Okay, so into this picture, quantum computing kind of introduces a fundamentally different computing architecture. It's not necessarily superior to classical computing, but instead it just offers a completely different set of trade-offs and opportunities, right? So the kind of promise of quantum computing is that for many algorithms, people have, you know, theoretical proofs that show that you can provide polynomial or exponential speedups. The sort of caveat to that is that, okay, usually these proofs rely on either noiseless or error-corrected, you know, quantum computers, which are still, you know, assumed to be many years away, probably. So the kind of major milestone was the announcement of quantum supremacy achieved by Google in 2019. This is basically a Google showing that, okay, they have a quantum computer that could solve a problem that would effectively be infeasible for classical computing. So that was kind of a major milestone and kicked off a lot of interest in quantum computing. On the other hand, something you have to keep in mind is that alongside innovation in quantum computing, there's also innovation in classical computing. So researchers have come along and then looked at Google's result and found new ways to do classical computing that could solve the problem that Google originally kind of demonstrated, right? So the kind of target that quantum computing is trying to reach is also a moving target because people do research on both sides. Okay. But a lot of companies now are kind of reaching the scale of quantum computers where they start to think, okay, maybe this could be useful for industrial optimization problems. In general, quantum computers are still small, which means that they're not going to be easily applied in a kind of general purpose way to any problem. But the way quantum computing researchers describe the current sort of state of technology is this idea of a noisy intermediate scale quantum era, where the idea is that, okay, if you have a very specific problem that's well matched to a particular quantum algorithm and quantum computing hardware, there's the potential for a valuable speed up in that specific application. And then the last caveat to mention is that often when people are proposing quantum algorithms and so on, there are kind of hidden overheads which you have to kind of keep in mind that, okay, maybe the algorithm looks really great, but for example, quantum computers often have a hard time loading classical data and things like that, so there can be these kind of hidden overheads that you only realize when you start to really implement things. Okay, so in the talk, I don't want to go too much into the details of how quantum computers work, but just to give you a flavor, I thought I'd have a slide on the qubit or the quantum bit, which is kind of the fundamental computing unit of a quantum computer. The idea of a qubit is that while it's in the quantum computer in a sort of coherent quantum state, it can have a superposition between the traditional classical states that we're used to with bits, right, of either a 0 or a 1. So it can kind of be partially in each state simultaneously. And then the idea is that when you measure the qubit, it will either measure as a 0 or a 1, and the probability of this is determined by these probability amplitudes associated with the states. And so this means that in this coherent quantum state, when you have 2 qubits, they can be in a superposition of 4 states, or if you have n qubits, they can be in a superposition of 2 to the n states. And so this creates some opportunities because, okay, although when you measure these, it'll still collapse down to an n-bit vector, while it's in the quantum computer, you're kind of doing calculations on these 2 to the n states. And the idea is that, okay, you can pretty much implement a qubit with almost anything as long as it's a controllable 2-level quantum system. So there are lots of different examples and competing technologies that people are developing, things like superconducting circuits and trapped ions and neutral atoms, which you can influence and control using lasers. Okay. So then when we get to the kind of computing level, there's different models of quantum computers. The most kind of general purpose one is the gate-based quantum computer that's in some sense analogous to what we're used to from digital computers that use logic gates. So you have these gates that are manipulating and entangling qubit states. And theoretically, these can implement any quantum algorithm. In practice, the noise level of the quantum system is going to limit the circuit depth that's achievable. Then there's another sort of set of computing models that are based on analog quantum computing. And the most popular one is quantum annealing. So this uses this kind of concept of the quantum adiabatic theorem to do analog computation. And quantum annealing is relevant for only a limited set of problems, but one of the problems that it can solve is something we call quadratic unconstrained binary optimization problems. So these are problems that have binary decision variables and a quadratic objective function and no constraints, which sounds quite limited, but interestingly, you can reformulate a lot of problems using auxiliary variables as QUBO problems. And with quantum annealing, because there's also noise in these quantum annealers, and you only have a limited time for annealing, the solutions you get are also going to be approximate. Okay. All right, so I want to talk about some of the kind of high-level opportunities for quantum computing in power systems. So one set of sort of opportunities is in this area of combinatorial optimization. This is probably where there's been the most interest and work, particularly because quantum annealing and quantum computers kind of lend themselves to these combinatorial problems, particularly in this QUBO formulation. So we have quantum annealing, and then on gate-based quantum computing, we have this kind of variational algorithms, including quantum approximate optimization algorithms. And we can formulate optimization problems as QUBOs, and then you can use these approaches to find hopefully good approximate solutions to these. Applications this is relevant for include unit commitment, network expansion planning, and also coalition formation, I mentioned, for energy communities or virtual power plants. Often you can think of these as cooperative game theory type problems, which kind of lend themselves to graph theory, and that links to this kind of QUBO type formulations. Okay, so interestingly, an area that hasn't been explored as much in power systems is this idea of using quantum computers for convex optimization. These are kind of further away because we would probably need larger and kind of lower noise quantum computers to deliver this, but there are proven polynomial speedups for semi-definite programming problems, and these are interesting because, as I mentioned, there's this kind of exact, under certain conditions, formulation for mesh optimal power flow with semi-definite programming. And so there's a quantum interior point method and also a quantum Aurora-Kale method that have been proposed. Caveats with these is that they require something we call QRAM, which is sort of theoretically demonstrated but not practically demonstrated, right? So we don't really have devices large enough to really achieve this. But the idea is, okay, it's down the track. In the near term, there are NISQ algorithms, so there are variational SDP solvers, for example, that could be applied to these problems as well. Okay, and then the last kind of major area where quantum computing could be valuable is machine learning-based optimization. So interestingly, in recent years, there's been a lot of power system research on how machine learning can help power system optimization, and it can do a bunch of different things. So you can use machine learning as an assistant for classical optimization. So for example, security-constrained optimal power flow problems try to have constraints associated with many different contingency scenarios, such as the failure of any device in the network. And so this creates a really long list of constraints in your problem. But then you can use a machine learning classifier to try and identify redundant constraints that can be removed from the problem, right? Another application that people have looked at a lot is using neural networks to directly emulate optimal power flow problems. So you basically solve an optimal power flow problem a ton based on historical data to train a machine learning model. Then in real-time operation, you can just run the neural network, as a one-shot to kind of get an approximate solution. And this can end up with a sort of millisecond solution time. And then also there's a lot of work on reinforcement learning. In particular, one of the challenges that I talked about for power systems is that our supply is becoming more uncertain. We're trying to control these nonlinear resources where we don't have very good models for them and so on. And so reinforcement learning, instead of trying to perfectly model our system and come up with optimal control, instead you use a sort of explore, exploit, and learning approach to explore a complex and stochastic environment and find a good way of dealing with the control. So quantum computing into this picture can help in two different ways. One thing it can do is it can speed up the training of classical models. So there are potential speedups for things like decision trees, support vector machines, and also Boltzmann machines, which are sort of a type of neural network. And then the other way it can help is that there's ideas of directly implementing sort of natively quantum machine learning approaches. So this kind of variational algorithms that you implement on gate-based quantum computers can be sort of conceptualized as a type of quantum neural network, because the sort of variation of quantum parameters and this kind of iterative optimization approach looks a bit like backpropagation. And then also there are some native quantum reinforcement learning algorithms as well. Caveats, particularly to the quantum machine learning models, training turns out to be quite hard without good initialization points. This is a kind of an area of a lot of active research. And the other thing is that there's often bottlenecks in trying to load data onto the quantum computer, which is a problem because, of course, machine learning is very kind of data hungry, right? Okay. Great. So I want to finish off by talking about a case study that we did looking at quantum annealing for combinatorial optimal power flow. So basically, D-Wave is a company that builds these kind of large quantum annealing devices. In particular, they have a 5,700 qubit annealing processor, which is accessible via a cloud platform. And then they also make available hybrid quantum classical solvers. And so we wanted to look at, okay, could these kind of devices solve some problem of potential interest in power systems? As I mentioned, the quantum annealers are specifically useful for solving QUBO problems, right? Quadratically unconstrained binary optimization problems. Which is not a problem that power system engineers normally would kind of look at very much, right? So the first thing you need to do is kind of formulate your problem as a QUBO, which I'll talk about a bit later. Once you've done that, though, the idea is that you need to embed the QUBO problem onto the quantum annealer. The quantum annealer basically has a sort of lattice of qubits which have the potential to be coupled with one another, and these couplings between the qubits are associated with the quadratic weights in your objective function. Now, ideally, a processor would allow for arbitrary coupling between qubits, but in practice, building a device that allows arbitrary coupling is very difficult. So in reality, they only have kind of sparse coupling between qubits. So you need to find something called a minor embedding, where you kind of take the original QUBO problem and then find an equivalent QUBO that is embeddable. The way you do this is basically by finding chains of physically connected qubits that together can represent a single logical qubit. Okay, and it turns out this minor embedding is kind of technically also a difficult optimization problem, but okay, D-Wave sort of has these like nice heuristic algorithms that seem, at least at the moment, to solve it quickly. Then, once your problem is embedded on the quantum annealer, this kind of adiabatic process sort of starts the quantum lattice in a known low energy state. And then the idea is by slowly changing the coupling between the qubits, the hope is that the qubits will remain in a low energy state as the problem sort of environment shifts towards the one of interest. And so at the end of the annealing process, the qubit states will correspond to the low energy state of your QUBO problem. But the solutions will be approximate because of noise and limited time and so on. Okay, so if we think about, okay, what's a problem of interest that we can try and embed, we wanted something that would be, that would kind of utilize the combinatorial solution characteristics of quantum annealing and could also be kind of useful potentially, but also small enough, right, to be potentially embedded. So what we kind of picked was a distribution network investment planning problem. And the idea is, okay, we're going to make decisions about sizing and placement of renewables, whether we want to, the selection between upgrade plans for the distribution network, and then also we have some electric vehicles with on-off charging. And then we have constraints in our problem associated with, voltage limits and electric vehicle charging limits and so on. Okay. So, of course, for the QUBO problem, one of the main issues is that you can't have any constraints, right? But in power systems, we always have safety constraints. So, okay, so you have to find some way of dealing with this. The way we deal with this is equivalent penalty terms. So you're moving the constraints into the objective function. And this is a bit of a science and also an art because there's kind of different formulations. And in general, you often need auxiliary variables to do this. If you do it well, you don't need many auxiliary variables. If you do it badly, you need a lot of auxiliary variables. So that's kind of the game. Linear inequality constraints can be included with a quadratic term in the objective, but you need to have auxiliary variables to provide slackness on the side of the constraint that's not enforced. And you can sort of develop a binary expansion of auxiliary variables to do this efficiently, and then the number of variables you need depends on the level of conservativeness that you want the constraint to hold with. Also, for some things like selecting between one of several discrete options, like one network upgrade plan, that can natively be included very easily with quadratic terms. One of the things we also found, though, is that for our network upgrade problem, we needed quadratic inequality constraints because when you upgrade the network, that will reduce the impedances, and then reducing the impedances will change how the power flows affect the voltages in the network. And you can do this by introducing auxiliary variables which are penalized so that they represent specific quadratic quantities, and then that lets you use, with those new kind of linear auxiliary terms, constraints to enforce inequality constraints on them. Okay, So the test case that we used was the IEEE European Low Voltage Test Feeder. We wanted to, so we had a time horizon of 24 hours with 1 hour resolution intervals. For planning, you would usually use multiple representative days throughout the year, but we want to keep our problem small, so we just looked at 1 day. We have 55 single-phase homes with, and we have up to 30 electric vehicles in the problem with, batteries around 100 kilowatt hours, 7 kilowatt charging, and we assume the EV owners have some value that they place on energy charged to their vehicles. We assume that energy, we sort of want to minimize the net import, the price of importing energy, so we have a kind of higher price of energy during the day on energy imports and a lower price during the night. And we assume there are 3 sites where we could invest in PV generation with either 25 or 50 kilowatts. And then we have network upgrade plans that could reduce the impedance of the network by 50% or 75%. All right, so on this slide, the figure that has the kind of orange and blue line, this showed how the size of the problem scaled with different numbers of electric vehicles and whether we include network upgrades or not. You can see that you have quite a fixed number of qubits. So you already need around 2,000 qubits just to embed the problem even with 1 EV. And you can see that the number of qubits then increases kind of linearly. But you cap out the number of qubits with only 9 electric vehicles without network upgrades and 5 with network upgrades. So this is kind of a positive and negative story. The quantum annealer is still quite small, right? But you can embed some problem of kind of interest. We also did a comparison between the time required for quantum annealing and simulated annealing. Okay, the problems we can solve are still quite small, but these are kind of indicative results. So we kind of to do a fair comparison. We made sure the simulated annealing was getting the quantum annealing was getting a better solution than simulated annealing. And one of the interesting things you get is that the simulated annealing, the time required increases significantly as the EV number increases. So it goes from 50 milliseconds up to around 120 milliseconds, whereas for the quantum annealer, it only goes from 50 to around 52 milliseconds. So you have some kind of early indication that there's quite nice computational scaling, right? All right, and then I'll went through these results because I'm running out of time, but just to show you that, okay, we solved a kind of larger version of the problem just to demonstrate the value of this type of thing at a kind of larger scale, so with 30 EVs. You can see on the left, there's the net import power. The orange is with network upgrades, where you reduce the impedances by 50%, which lets you include an additional 50 kilowatts of PV generation. And this kind of shows that what you get is more ability to export renewable generation during the day, and then at night, more ability to charge the electric vehicles. And the right-hand side shows that across the different phases, the voltage limits are basically almost perfectly installed, and that's despite having our linear model and also our approximate constraints and so on. All right, so I'll skip through that and jump to the conclusions. So in conclusion, we have a paper which in Joule, which describes this kind of opportunities for quantum computing in a bit more detail. The 2 main takeaways I want to leave you with. One is that net zero makes optimization increasingly important and challenging for power system operation and planning. And the other is that quantum computing can offer value for quite a wide range of different problem types. Areas for future work that we're looking at, one is the opportunity for nearer-term impact with hybrid quantum classical computing. So the idea here is that, okay, with these kind of noisy small-scale quantum devices, they're not going to be able to solve large-scale problems, but perhaps as a kind of dedicated accelerator within a wider data center, they could provide some value. One area that's really needed is benchmarks, particularly for NISQ algorithms, where we don't have proven speedups. And then more broadly, there's kind of a desire from power system operators to do innovative computing, but there's lots of different innovation that's happening in different directions. And so one of the things we proposed in the paper is the need for a sort of holistic computing R&D strategy for power system operators to integrate different innovations that have different timescales. So on the longer timescale, we have quantum computing, but on nearer timescales, we have things like GPU computing and also cloud-to-edge computing. And probably all of these can help one another, but we need to think about how they integrate. And then the last thing is that I'm co-chairing a new Power and Energy Society task force in this area with Professor Yan Li from Penn State. So yeah, please get in contact if you're interested in participating. We'll probably have some webinars and events in the upcoming years. Thanks very much.
Thank you very much, Thomas, for this very inspiring talk and also showing us a case study of using a quantum annealer. So I can imagine that there are a lot of questions in the audience. Yumi, and so you will walk around with the microphones. Oh, I can also walk around with a microphone if you have a question.
Oops. Thank you. So brilliant talk, and I like this case study about putting this on the SDWave machine. What are your thoughts about putting this on a gate model machine? Is this somewhere in the near? Are there algorithms for that?
Yeah. So actually, so we have a collaboration with researchers at E.ON who were interested in a different application that I mentioned more recently, so looking at energy community coalition formation and sort of graph theory problems for that. And so we have a kind of preprint with them where, it's quite nice because they have sort of relationships with IBM, so they can really trial gate-based algorithms on the kind of big IBM computers and so on. And they actually do some comparison between like quantum annealer versus different gate-based options with these quantum approximate optimization algorithms and so on. So yeah, you can, so definitely going forward, you kind of need to be able to compare the different quantum devices and different algorithms against each other. Yeah.
Hey, well, thank you. Yeah, very interesting. I was wondering, because I saw you compared the quantum annealing with the other algorithm, also quantum, but I was wondering, like, comparisons with traditional computation first. That's one question. Yes. Maybe if I can ask another one.
Sure.
And I was also wondering if there's applications. So I see this is the optimal power flow. Have you seen, or are you interested also in like stochastic optimal power flow? This kind of applications. Is it also could it also benefit from quantum formulation? Thanks.
Great, yeah. So the comparison I showed was between quantum annealing and simulated annealing. So simulated annealing is in some sense a kind of, it's a classical algorithm where it's kind of, what would you say, trying to replicate a kind of analog process of kind of how a thermal system would cool down. And so it's quite interesting because actually there's a version, people used to talk about quantum annealing, meaning a classical algorithm that was replicating what a quantum computer would do if it was doing quantum annealing. Now actually we have quantum annealers that can actually do quantum annealing, if that makes sense. But in some sense they're both, the idea is that they're both basically heuristic optimization algorithms for solving combinatorial problems where there isn't really a good theoretical algorithm for solving them. So in that sense, it's kind of a classical version in a sense. Yeah, so the point on the stochastic optimization, definitely. So one of the areas my group does, work on is chance-constrained optimization. So kind of for uncertainty-aware dispatch. So how do you think about, okay, say we want to dispatch the power grid, but in the context of lots of renewables, or we want to coordinate these flexible grid edge devices. But of course, in detail, if you're an electric vehicle owner and the aggregator is trying to get flexibility from you, you might get caught in traffic, and so your EV isn't available, and so on, right? So really, in reality, there's a lot of uncertainty. There's different approaches for dealing with that, but all of them basically increase the complexity of the optimization problem. So they tend to add, additional constraints, maybe additional decision variables, and so on. So in that sense, it makes the problems more complicated, yeah.
Yeah, thanks for the presentation. I was triggered by the last slide where you said there are other ways of computing GPU and so forth, cloud. I think this is really being aware of the semantic gap of your problem and your compute hardware. You use the annealing trick now. Yeah? You have a hammer and you translate the problem to annealing. I've seen an example recently where a complex problem was suddenly found to be translated to matrix multiplication. So off you go with GPU. Suddenly it was mega fast compared to. But I think if you have a very complex problem, and you talked about that, with transport and energy, and you have uncertainty and combinatorial explosions. Probably you really have to decompose it as you mentioned. But what type of language and tool chain and theoretical foundation would you envision to do that? Because you have to track down, or you have to identify that part is a candidate for this type of computational trick, and maybe compose and translate the problem in a very targeted way for the hardware. So what types of tools or methods would you envision to do that?
Yeah, I think it's really interesting. I think so. I guess the way I would say it is that I think this is kind of a big challenge for the power system research community, and then probably the operations research community interacting with the power systems research community. Where really what I would say is that at least my experience with system operators in the UK, particularly the transmission system operator in the UK, is that maybe when I first moved to the UK, in 2016, there wasn't as much awareness of, there was not very much interest in even AI kind of at this sort of transmission system level, and there wasn't really, they were very suspicious of kind of even optimization in general. They were much more focused on, okay, but we have these kind of guys in our control room, they know how to operate the system, maybe they have some analysis tools they can use, but they're not really, we don't really have this automated process. Now they've really changed their thinking, and they've gotten on board with optimization, and to some extent with kind of AI, at least for forecasting and so on, and they have a process at the moment to look at architecture for what they call a kind of grand optimizer for the system, at the transmission level. So they are moving towards automated optimization. But I still think there's a kind of another gap, which is that they haven't kind of incorporated at a deep level this idea of computing acceleration, where maybe, in other areas we have this idea of, okay, there's GPU computing, there's quantum computing, there's new edge computing technologies and so on. So I think that will be, once they move to this kind of automated dispatch, then I think there will be this kind of need for more architectural thinking and more like a roadmap going forward. But I would say that, that's probably something that's still in, researchers kind of understand the need for that now maybe, but maybe the industry hasn't quite, at least in the UK, maybe hasn't quite gotten up to that point. So yeah, I think it's, it's an area where there's the need for kind of dialogue and discussion about the need for an architecture. And then of course after that, then there's the question of what the architecture looks like, or what is that kind of frameworks that would allow you to make those decisions look like, yeah.
Yeah, so we were talking about the integration of quantum computing with GPUs and high-performance computing. Do you think that is the decision of how to use those different kinds of computing is up to the end user, or will it be up to the computing providers, service centers, or even the quantum computing providers? Yeah.
Okay, yeah, it's very interesting. So my experience in this area of kind of, say, like innovation projects for, energy systems and so on, right, is that and particularly in the kind of era that we're moving into, where we're thinking about, okay, there's new devices, but that opens up new opportunities for operation, but the value of, say, flexible operation is really very determined as well by the kind of physical infrastructure you have in terms of lines and so on. And then on the other hand, this is all directly impacting people's lives, because we're talking about the reliability and cost of their energy, and also the devices they have in their house, like they're moving from a car to an electric vehicle and so on. So somehow there's lots of different stakeholders, right, in any of these kind of like energy optimization type problems. So usually what I found is for innovation projects, you need a kind of consortium of stakeholders involved in the project. So you need a network operator who kind of needs flexibility, but then you also need some kind of tech provider or flexibility aggregator who can really engage with the details of the technology and the algorithms and so on. But then you also need some kind of actual devices to optimize, right? So you either need the community involved, and the community wants to have electric vehicles or that kind of thing, or you need maybe some big like a smart campus or something like that involved. So I think you need the kind of end users, system operators, and technology providers all working together to really kind of understand the problems and so on. And that can work quite well in a kind of like cooperative, sort of consortium innovation project. The big challenge I think we've kind of found is, okay, how do you then turn that into business as usual and create something that's kind of scalable across the grid? And I would say at that point, I think there's still a bit of a gap maybe, but I think people have gotten quite good at doing these kind of innovation projects, at least in specific areas with specific sets of stakeholders, yeah.
I would also have one question. As universities, we also have an educational task. And I think quantum computing is maybe not the most obvious course in an electrical engineering or in a mechanical engineering curriculum. So maybe it's more rooted in quantum physics. So do you have some recommendations, some advice how to get, let's say, quantum computing as a tool into electrical engineering curricula?
Yeah, so it's very interesting. I mean, I think that's a kind of for me, that's a kind of a real-time challenge, right? Because I'm sort of started now having PhD students, who are going to kind of enter into these areas. And for me myself, I come from a power system engineering and control background, not a quantum computing background, right? One of the things that's interesting is that I remember talking to a control professor when I was doing my PhD, and that was long before I had any interest in quantum computing. But I remember him sort of saying that, like when he did electrical engineering, somehow quantum mechanics was an obvious component of his sort of degree back in maybe the 70s or something, and that somehow that's been lost from the curriculum. So perhaps actually that kind of core physics, right, would be a nice thing to add back maybe into engineering now. And the other thing is that when I was doing my degree, at the University of Melbourne, actually the focus of the degree was much more on control and digital electronics and so on, but really there was very little power engineering at all kind of thing, because I think it was just before, this kind of topic of net zero and energy transition and stuff had gotten big enough for it to then be reinstated in the curriculum. And since then they've now gotten professors of power engineering, and they've really increased that size of the program. So I think there's a big kind of question about what engineering curricula should look like. But I think that interdisciplinarity and working with quantum researchers, right, and doing these kind of collaborations with experts and mathematicians and so on is clearly something that's needed both at the teaching level and research level. Yeah.
Any further questions? So,
Thank you for the very good presentation. I have a question. From what I understand, quantum computing is not like a separated one. You always need a, let's say, regular computer or a normal. Yeah, the current computers we have, they are connected to that quantum. So there is a transition, like you have the problem, you pass it to the quantum, and then you get it back. So I wonder if you can say a few words on that, if it's right my understanding. And then I'm coming, let's say, from a security perspective, and there is a, security of supply these days, I don't want to get into details like state attacks on energy world and stuff. Probably it's a very early question, but I wonder how do you see this, because having the interaction with the regular computers is like, have anyone thought like, okay, this is something to be, protected or taken into consideration. Thank you.
Yeah, sure. So in terms of the interaction with a kind of classical computer, I suppose, right? So my understanding is that I guess the kind of, there's a sort of fundamental aspect, right, of kind of, quantum mechanics or something, right? Which is that we can have the qubits in a sort of coherent quantum state when they're kind of in the quantum computer. But the point is that as soon as we try and actually measure the qubits, they will collapse back to these kind of classical states, if that makes sense. So no matter how you build the kind of quantum computer, you can't sort of directly access the quantum states. You can only kind of observe the probabilities through running the algorithm multiple times or something like that. So there's this kind of necessary interaction between the quantum world and the classical world that we're kind of used to, I suppose. So there's some kind of fundamental interaction there. In terms of security of supply, I guess there's kind of, so I guess there's security of supply. Maybe when people are talking about quantum computing, they're often worried about cybersecurity and there's this element of quantum computing that could be used for kind of cryptographic type issues and so on. I suppose, security of supply in this kind of optimization context, right, introduces its own set of problems around resource adequacy and this kind of expansion planning that's dealing with kind of security. So you could take your question in different ways, I guess, yeah.
Thanks very much. I think in view of time, we also should close it here. Yeah. So I have a little present for you.
Yeah,
thank you.
Thanks very much.
And a big applause.
Yeah, thanks, appreciate it. Thank you. Thanks very much, great.
And so now we have a short break of some 10 to 15 minutes. Take a caffeine shot, take coffee, and we see you back in 10 minutes from now.